Hello and welcome back. In this tutorial, we will show you how you can use the software to design stable feedback control loops. This is a multiple output power supply using a top switch JX device. It has a 5 volt 3 amp output and a 12 volt 1 amp output. It uses a secondary side TL431 to regulate the output, with the 5 volt output set as the main output. PI Expert offers several feedback options, but the two most important options are the secondary side feedback using a simple Zener reference and the secondary side feedback with an error amplifier like the TL431 shunt regulator IC. Right-click on a feedback component and then click on the functional dialog. This opens the feedback dialog. This particular design uses the TL431 feedback option. Just a quick mention that you can also change the feedback type to say a secondary Zener feedback through the Design Options dialog. I'll hit Cancel for this design and navigate back to the Feedback Components dialog. As you can see, a detailed feedback circuit is suggested along with recommended values for the components. These values are calculated such that the crossover frequency is achieved at a minimum phase margin of 45 degrees. In this example, we have an estimated phase margin of 99 degrees. Clicking on the Chart button opens up a Bode plot showing the gain and phase plots against frequency. This chart gives a better feel for the overall performance rather than going on the values of crossover frequency and phase margin alone. After all, loop stability is all about the shapes of Bode plots. I'll close this chart and then go back to the Feedback Components dialog. Let's review some of the feedback elements and what role they play in the stability of the closed loop. The main compensation elements are RF2 and CF1, which form a zero at low frequency, typically around 100 Hz. Additionally, another compensation pole is derived inside the top switch and is located at around 7 kHz. This pole also serves as a noise filter for the controller within the top switch. This pole-zero pair forms the basis for the phase compensation of the loop. The gain of the loop can be adjusted by varying resistor RF3. For example, if I increase the value of RF3 to 1.2K, I can expect the crossover frequency to reduce somewhat. If you think you made a mistake, you can always click on the default button against any component to go back to the original value. The phase boost network is a RC network placed across RF3, and it boosts the phase around the crossover frequency if it is required. When you optimize a design, the software automatically makes initial calculations based on the primary inductance and output filter capacitor values, and presents you with a recommended circuit for a first prototype. The Soft Finish button opens up the Soft Finish dialog. Checking this box activates the Soft Finish circuit. A Soft Finish capacitor can help reduce overshoot during startup. Click on the Dual Outputs Control button to open a dialog through which you can assign dual feedback for this design. The ratio of V main and auxiliary signals helps to specify the amount of feedback signal that should be derived from that particular output. For example, in this design, we can assign that 75% of the feedback signal come from the 5 volt output, and the rest 25% can come from the 12 volt output. The two resistor values are updated as shown on the dialog, and they will also be updated on the main schematic as we will see in a moment. Click OK, and then OK again. Let me zoom in and focus on the feedback section so that you can see it more clearly. See how the feedback section has been updated to show a dual output feedback. The soft finish circuit can be seen as well. For more information on control loops, please see application note AN57. Thanks and good luck.